All right, in our second example, we're going to look at what happens to a line under the z-squared function. So in particular, our set S in this case is going to be a line, or actually we'll use C because it's one-dimensional, C for curve. And it's going to be the line x equals 1. So it's going to be the z's in C such that the real part of z is exactly 1. Or if you like, it's the collection of all 1 plus iys, where y can be any real number. You know, they both mean the same thing. All right, so we're going to compute the image of the line under z squared, and in this case, we're going to just go algebraically. I think that's easiest. One thing to point out, though, if you were to try to see what happens to it just geometrically, is that the squaring function doubles your argument and squares your modulus. So what's going to happen? Well, let's try geometrically first. So um, let's draw C. So C is a vertical line where x is 1. So here's C living in the z plane, which is the domain plane. And then we're going to apply the squaring function to it. So f of z is z squared. And when we square, what's going to happen? Well, if you take a moment and you think about the possible arguments of points on C, as you go further and further up, the ray that joins the origin to that point is getting more and more vertical. And so you're actually going to achieve all arguments from on this portion of C from 0 up until pi halves. You'll never actually be pi halves because you'll never be vertical, but you'll get real close. And then similarly on the bottom part of C, you will have all arguments from 0 to negative pi halves, but not equal to negative pi halves. Again, you're never going to be equal to it. You're just going to get real close to it. So your arguments are going to vary between negative pi halves and pi halves. So let's write that down. So args, oops, let's not use red. Now what happens when we square C? Well, we have to double the argument. So the argument of z squared is going to go from negative pi to pi. So we're going to get all possible arguments. Well, excluding pi, but we're going to get all arguments from negative 180 to 180, non-inclusive of the endpoints. Great. Now what happens to the modulus when we do this? Well, 1 plus iy gets arbitrarily big and arbitrarily, goes to infinity in the other direction as well. So the modulus of 1 plus iy gets arbitrarily big. So what's going to end up happening is on the w plane, let's see what's a good color. Let's use blue. On the w plane, 1 squared is going to be 1. That's fine. And then as we go upwards on in the domain on C, our argument's going to get bigger, but we're going to start to curve because we have to get all angles from negative pi to pi. And then similarly, as we go downwards on C, our distance from the origin is going to get bigger, but we're going to start to curve because our argument is sort of going in a linear way, whereas our modulus is not. It's going in a quadratic way. So this is going to be what f of c looks like. It's going to be a parabola. Now let's find that algebraically to verify our intuition with this problem is correct. So what's f of c? Well, f of c is a collection of all f of 1 plus iys, where y is any real number. And f is the I will square you function. So it's a collection of all 1 plus iy squareds, where y is a real number. And 1 plus iy squared is 1 minus y squared plus 2y, where y is a real number. All right, 2yi. And so what is this? This is this. If we were to look at the real part and the imaginary part, since I already used x and y, let's use u and v. What do we know? Well, I think if we take v squared, we're going to get 4y squared. And then if we add on to that 4u, we're going to get 4y squared plus 4 times 1 minus y squared. And so the negative 4y squared and the 4y squared cancel, so we get 4. Okay, so in other words, we have the equation v squared plus 4u is 4. And we could write that a little bit differently. We could write that as 4u is negative v squared plus 4. Or finally, u is negative 1/4 v squared plus 1. If u is the x-coordinate and v is the y-coordinate, this is a parabola that opens to the negative x direction. So it opens to the left. It passes through 1 as the vertex, and then it has some stretching parameter that we could graph if we wanted to. But let's just verify that's what we got. So if we go up here, it opens to the left. It's a parabola that opens to the left. It passes through 1. When v is 0, we get u is 1. And that's it. So we found it. So in this case, the image of a line is a parabola. So image of x equals 1 is the parabola, x equals negative 1/4 y squared plus 1, or you can keep the u and v variables. It doesn't matter. And this is this shouldn't be at all surprising, even irrelevant of this problem. So let's go back up just one more time. So in this problem, what we're looking at, there we are, is we're seeing what happens to a line, something that looks like y equals mx plus b, when we square it. Well, usually what happens when you square a line is you get something quadratic. And since the line goes off to infinity, it can't be like an ellipse or a parabola, something like that, or ellipse or a hyperbola. Ellipse or a circle. It can't be a hyperbola because a hyperbola has two pieces. And that leaves open one option. It leaves open the parabola. So it's really unsurprising that we get a parabola here.